Kryss Waldschläger talking to us about some very modern component of source to sink, namely plastics, and how plastic transport might do some very funny things compared to sediments, and might also be comparable to sediments in some other ways. I think we'll hear much more about that in the next hour. But before that, let me move to the next slide. Probably most of you know that already, but for those of you who don't, there's a great YouTube archive of a lot of these talks. So please visit that. And there's also a Bilibili space for that. And then you can follow Pohl on Twitter for announcements of upcoming talks, including a talk next week by Craig Smeaton from the University of St. Andrews, talking about sedimentary systems and the carbon cycle. So please join us next week as well. And with that, I'd like to introduce Kryss. Kryss has received her degrees from Aachen University in Germany in civil engineering, bachelor's, master's, and PhD. And after that, she moved to the Netherlands, to Wageningen University, very close to Utrecht University, where I am. And at Wageningen, she continued her research looking into transport behavior of microplastics in the aquatic environment. Of course, a very important topic these decades. So please, Kryss, if you can share your screen and get started.
Sure.
Stop share.
Let's see. Now you should be able to see my presentation.
Yes, we are.
Great. Let me just close you. Okay. Yes, yeah. Thank you very much for this nice introduction, and thanks for inviting me to giving a talk about microplastics here. I think it's the first one on microplastics in this webinar, which is great. So today I want to talk to you about diverse microplastics and where to find them, or to frame it a little bit more scientifically, what we can learn from natural sediment when it comes to microplastic challenges. And I want to start with my general motivation behind my research. So microplastics are everywhere. We found them on Mount Everest, we found them in the deepest sea, we found them in rivers and lakes in Antarctic and the Arctic. And I hope we can all agree that they don't belong in the environment. And so far it is that easy, but I would like to start with a perhaps a little bit provocative statement. I believe that the most important question right now is how are microplastics transported? And let me explain that. So there are several aspects of microplastic research. One of those is environmental sampling, or monitoring to assess the actual pollution levels in the environment. Another one is risk assessment, where we want to assess the actual threat that microplastic poses. So the toxicity and the exposure, which again depends on the environmental concentrations. And then we have mitigation strategies. Of course, we want to reduce plastic pollution in the environment. And I believe that all of those aspects are closely related to the transport behavior. So where do we need to sample? How can we extrapolate the sampled concentrations? How high is the exposure to, for example, benthic organisms? And where should mitigation strategies act? Just to name some of the questions that are connected to the transport behavior. And this is particularly important for the dynamic fluvial environment. Research there started only in around 2010, and it mainly focused on the detection of microplastic in rivers. So transport is a very, very new topic for microplastics in rivers. So what we did in the past is we used transport models and theory from sediment transport. And the aim of my research is kind of to assess if this is actually suitable, or do we get correct results if we use the knowledge that we have on natural sediment transport and use that for microplastic particles. Now, if we look at the publications that are, for example, in this case, in the Web of Science, it should actually look a little bit more like this. You can see that we have decades, and you all know, of course, we have decades of studies on sediment transport, while microplastics just recently started. And if we now understand publications as knowledge, then we clearly have more knowledge on sediment transport than we have on microplastic transport. Okay, so let's look into that a little bit more closely. When we compare the particle properties, maybe a quick disclaimer for those that are not that familiar with microplastics. We're still struggling with a uniform definition of microplastics, especially when it comes to the size. So the size range is something that I use, but you will also find publications that use 1 millimeter as an upper size limit, or some that use, for example, 300 micrometers as a lower size limit. So just keep that in mind. Now, if we compare the size, you can see that it is similar to the natural sediments clay to gravel. You all know that clay is transported in a different way than gravel. And that's something, so considering cohesive transport is something that we haven't done for microplastics yet. When it comes to density, well, it is a little bit easier. The density of microplastics is buoyant and non-buoyant, which is maybe the biggest difference that we can see to mineral sediments. And then the last property that I have here is the shape. I know that natural sediments are not all granular, but as far as I know, that's how we often simplify them. So if we compare it here, microplastics are simply more diverse. We have pellets, we have fragments, fibers, foams, and foils, and I will tell you a little bit more about that later on. But for now, this should be it. So learning from natural sediment transport, it does make sense in principle, but we have to be careful. And having that in mind for quite some time, and knowing how broad this topic is, I tried a new way of collaboration, and I asked on Twitter if someone wants to join me in writing a paper. And 25 awesome researchers actually responded to that, and I've seen some of them here in the meeting. And together we wrote a very nice review paper, which hopefully will be published soon, that focuses on the particle properties, the aquatic transport dynamics, the sampling techniques, and ecotoxicology, always by comparing microplastics to natural sediments. And we've derived 7 research goals with relevant tasks that we need to achieve to finally understand microplastic in the aquatic environment. And my following talk is a little bit based on this paper, so just so you know. I would like to start with the particle properties. We know that they are important for the transport behavior, but we can't really define them yet. And when we start with the size, how do we define the size of a particle? Well, first, there are 3 main dimensions. So the longest, the intermediate, and the shortest side length. And which one do we actually use? Well, for microplastics, it's often the longest side length. So we say particles are supposed to be smaller than 5 millimeters. But does it really make sense? I don't know, something we should discuss in the future. The second big question is, how can we actually define 3-dimensional particle side lengths? Of course, you can do it manually, but then you will probably always get different results. You can do it with imaging techniques, but then you often just get 2 dimensions. And especially if you want to look at a huge number of particles, it gets more complicated. What we do for sediments is using probability distributions like day 50 or D90. And I was wondering if we can actually use that for microplastics as well. And I tried to create grading curves for microplastics, like the ones we know for sediments, but it is difficult at the moment because we have to base them on environmental studies, and we often only give particle amounts per size. So I could tell you that we have 100 particles with a size length of 10 micrometers, but I can't tell you the mass of that. And that makes it difficult to create those grading curves. The density, well, it's a bit easier, but it's still difficult because we deal with time-dependent density variations due to aggregation, biofouling, or fragmentation. And we don't know if we have to include them in transport models or how to include them in transport models. And this does look like a small thing, but we do find microplastics that are buoyant or originally buoyant in the sediments in rivers. So how did they get there? Did the density change? And we do have some studies saying that biofouling can actually make buoyant particles non-buoyant. So it is always important to know that there are different densities for microplastics. We have the initial density when the particles are produced. We have the environmental density when we have biofouling and aggregation that might be completely different than the initial density. And then we have the lab density. So if we take particles out of the environment and measure the density in our lab, there are some processing steps in between, which again changes the density. So the question is, how comparable are those types of densities and which one is the most important one? And the last particle property I want to talk to you about is the particle shape. And why is it even important to define the shape of a particle? Well, for sediments, we use it to predict transport behavior. And for that, we often use geometric standards. For microplastics, we use a shape to identify the origin of the particle. So we know that pellets are mainly from production sites or are lost during transport, while fragments fragment in the environment from bigger plastic items. And that's what we used the shape in the past for. But we can't really use the shape definitions that we use now for plastic transport. For example, if you look at the category of foams, that could have any shape. It could be a pellet, it could be a fragment, and that makes it more difficult to compare different studies. The same goes for pellets. On the left, you have 4 pictures of pellets, and they all look different. So you don't really know how they are transported. So I think that we need to improve how we describe microplastic shapes. And for that, there are several suggestions in literature. Some use the main dimensions, some use the relative ratio of the main dimensions, and some use shape descriptors, like the Corey shape factor, the roundness, the flatness. You might know those from sediment transport. Now, in the end, we need to define the particles that we have. And we need to do it now and not somewhere in the future. So I will show you what I did in the past. And well, I did it when I started my PhD, so I might do it differently now, but still. So I manually measured the significant side lengths. That sounds easy, but do it to a particle like this, and it gets more complicated to identify the different significant side lengths. Then I calculated the equivalent particle diameter. I used this equation, but you could also use a different one. Especially when we're talking about fibers, it becomes more difficult. For determining the density, it's a little bit easier. We have norms for that, and my particles were new, so no biofouling, no aggregation, nothing, so it was quite easy. And then in the end, I used shape descriptors, like in my case, the Corey shape factor and the Powers roundness. And there have been some studies that say, well, they came out later, they say that there are other important shape factors that we need to include, like the sphericity, elongation, flatness, aspect ratio. But we're still not completely sure which ones are really important to define microplastic particles. So what we did is we derived in our paper research goal number 1, which is to improve and standardize descriptions of microplastic particles. Now, let's talk about microplastic transport in rivers, which is more my topic. We start with one basic assumption. Microplastics can be transported downstream in rivers. And the second assumption is, because of the densities, which I just explained to you, microplastics can be transported in 3 different transport modes. We have surface load, we have suspended load, and we have bed load. And we looked into that in more detail by applying the Rouse model on microplastics. And we used as many microplastic-specific input parameters as we were able to get, but there were quite a lot that are still missing. And for those, we used the basics from sediment transport. So it's important to be aware that the use of the Rouse model for microplastics, it has not yet been validated with physical experiments, which is something that we're doing right now. But I don't have the results yet. Okay, so in general, however, we were able to show that microplastics are in fact transported in all 3 transport modes, and that they, well, we didn't prove that, but it was also nice to see that they've also been observed in all environmental samples in all of those transport modes. And we could use this to get a first understanding of the vertical distribution of microplastics. But this preliminary understanding, we need to improve that with more studies. And it is highly dependent on the settling and rising velocities. So I was wondering if we can maybe use the Stokes equation to describe the settling and rising velocities of microplastics. So I went into our lab and I did some experiments. And I used a settling column where you could let particles in from the top and from the bottom. And I tried to vary the particles that I look at to include, well, most particles that we can find in the environment. Of course, it's always difficult, but here you can see that I used the most common polymer types, the most common shapes, and that the density were both lighter and heavier than water. Now, I don't want to go into detail with the results, but I want to show you the comparison of my results to the sedimentological theory. So most of you will probably know Stokes. Some of you might also know Dietrich, and then there are some other settling velocity calculations that we know from sediment transport. And what you can see is that the error between the empirical results and the theoretical calculations is quite high. And that is especially true when it comes to fragments and fibers. And I think we all can agree that an error of over 200% is not good, and it's not suitable to use those calculations. So what I did is I derived a new theoretical approach to describe settling and rising behavior of microplastics, which is based on the Stokes equation. So I only adapted the drag coefficient for microplastics, and the figure on the right shows that the results are quite suitable, which is nice. I was happy, and then I realized, well, it is not really that easy, because in the environment, we have other processes. We have the interaction with environmental substances and forces. So we have degradation, we have aggregation, and we have biofouling. And I've already told you that that influences the density, for example. So it will probably also influence the settling velocities. Okay, so I repeated my experiments with environmental microplastics. And luckily, well, for me, this parameterization was still suitable for most of the environmental microplastics. However, it was not suitable for microplastic films, which you can see in this figure with a light blue. And that was because I didn't include films in my original experiment. Because when I started it, it wasn't that clear that we also have so many films in the environment. And we believe that this parameterization is not usable for foils because of the deformability of the particles, because they change their shape during settling and rising, and that's just not included in the formulation. But we have been working on looking into that in more detail, and there will hopefully soon be a paper also including the settling and rising behavior of foils. Okay, however, there are even more processes to consider. We have turbulence that influences the vertical distribution, and we have entrapment in vegetation. Still something we need to look to in the future. So next, I want to talk to you about the onset of motion. Here it really makes sense to look at sediments, because we were able to link the occurrence of microplastics to the occurrence of finer sediment fractions of sediment. So where there was more microplastic, there was also more sediment. And maybe a quick recap on how we look at resuspension for sediments. We often use the Shields parameter, which is well dependent on the particle diameter, the density difference, and the shear stress of the particle. We also use the hiding exposure effect, which is for non-uniform sediment beds, where smaller particles hide behind bigger particles in the sediment bed, and bigger particles are exposed to the flow. And I believe that this is more suitable for microplastics, so I included this in my study. Now what I did is I went to the lab, and at my old university at RWTH, we had the perfect experimental setup for this. This so-called annular flume can create an endless flow by rotating the cover and the flume in opposite directions. And from previous studies, we know the flow velocity and the shear stress at the bottom of the channel, and can increase that systematically, which is, well, it was quite nice for this experiment. Now, I know that microplastic particles in the environment are rarely lying on smooth flume beds. So I installed some different sediment beds. Here you can see that they were ranging from medium sand to fine gravel. The first three are uniform, and the last one is a mixed sediment of the three others. And the results were quite interesting. I was able to show that with increasing microplastic density, the shear stress also increased. Well, I mean, that makes sense. The heavier a particle, the higher is the shear stress. I was also able to show that with higher sediment diameters, the shear stress also increased. This was quite interesting, because I didn't know about that before. It was easier to imagine that that bigger microplastic particles had a higher shear stress. And I wasn't able to show a statistic correlation between the microplastic shape and the shear stress. But when I looked at the videos that I took, it became clear that, for example, fibers, they got stuck in the pores, and which led to higher critical shear stresses, because they had to jump out of the pores to be transported. While spheres and pellets they moved earlier because they were able to roll. And I'm pretty sure that there is a connection, but we need more experiments on that to prove it. Now, what I did, I included my experiments, my results in the Shields diagram. And I'm sorry that it is red and green. I know that's not very inclusive, but I created this figure before I knew that. So in the Shields diagram, you can see the Shields curve, which divides the diagram into a part of motion above the line and an area of no motion below the line. And by adding my results, I was expecting all of them to be above the line, so in the part of motion, because, I mean, the particles did move. But you can see that most of the particles were actually below the line, which, well, for me, it indicated that the microplastic particles are remobilized much earlier than we previously thought. and that they might have a higher mobility in the fluvial environment. So now I wanted to use this for the future. And for that, I adapted the hiding exposure effect by adapting the coefficient. And now we're able to describe the critical shear stress of microplastic particles in dependence of the particle diameter and the sediment bed grain size. So what have we learned so far? We know that microplastic resuspension is influenced by microplastic particle size and the shape, although I couldn't really show that, but well, it is dependent on the size distribution of the sediment bed. We've also seen that the Shields diagram is not really suitable for microplastics. What we don't know is how biofouling influences the resuspension behavior and how the shape specifically influences it. So something to do in the future. Now, some of you might say, well, in the environment, the microplastics, they're not really lying on top of the sediment bed. They might be buried or infiltrate into the sediment bed. Yeah, that's what I also thought. So I did some experiments on that. And I wanted to compare microplastic infiltration with fine sediment infiltration, because that's suitable for particles with less than 2 millimeters diameter. And I think that, well, it sounded like microplastic. So for fine sediment infiltration, we have two processes. We have the unimpeded static percolation, where the particles can infiltrate to the bottom of the sediment bed. And we have bridging processes, where we have one finite depth infiltration, where the particles can infiltrate to a specific depth, and fine surface sealing, where the particles don't really infiltrate at all. So here you see my experiments. I used the sedimentation column, and I added glass beads in different compositions. You can see uniform glass bead compositions and bimodal compositions. And then I added different microplastic particles and irrigated this column for 1 hour. And after the experiment, I manually removed the glass beads and layers to determine the infiltration depth of the particles. And here you can see my results. I know it's a little bit difficult to understand, so let me run you through it. On the left, we have the different glass bead diameters increasing from the top to bottom. And then I divided the microplastic particles in the different shapes. And the darker a square, the further did the particle infiltrate. And what you can see is that the microplastic diameter led, that an increasing microplastic diameter led to lower infiltration depths, which makes sense. The bigger a particle, the less it infiltrates. And it's the other way around for the glass bead diameter. So the bigger the glass beads, the higher did the microplastics infiltrate, because the pores were simply bigger. Again, the microplastic shape didn't really influence the infiltration depth. But when we look at fibers in specific, we can see that the fiber diameter, the thicker a fiber, the less it infiltrated, while the fiber length didn't have any influence. And I think that's very interesting. And after my experiments, I realized it might be due to the shape descriptors that I used that might not be suitable for this statistic analysis. Well, something to learn for the future. Now, comparing infiltration of microplastics to natural sediments. For that, we need to look at the ratio between the particle that is infiltrating and the particles of the sediment bed. And we have those three categories from fine sediment infiltration. And when I clustered my results, it became clear that it did fit quite nicely. So on the left, we have the particles that are infiltrating quite a lot. And on the right, we have the particles that don't really infiltrate at all. And then we have in the middle this this mixture of both. So how can we use that in the future? Based on this analysis, I created a matrix which we can use for defining places where we should take depth profiles of microplastic concentrations in soils. We need to take those because we want to understand how microplastics are, where they are in the sediment. But it doesn't really make sense to do that everywhere. Because let me give you an example. So if you're able to identify microplastic particles down to a size of 10 micrometers, and your sampling finds sand, then it does make sense to take depth profiles because the microplastic can actually infiltrate into the sediment bed. Of course, all of this, what I'm explaining right now, is only on infiltration, not on burial, but we need to look at that in the future. Now, if you're only able to identify particles down to 100 micrometers, which is really often the case, then it doesn't really make sense to take depth profiles because the microplastic can't infiltrate into the sediment. Okay, so that is all still very rudimental. We definitely need more studies that, for example, just use natural sediment for the infiltration experiments. But that's something to do in the future. The last topic I want to talk to you about is numerical modeling. And we do use numerical modeling quite a lot. We have 0D and 3D models. We have models that are on a very small scale. We have models that model the entire world. And a lot of those models are based on sediment transport models. Now, based on what I just told you in the last half an hour, I'm not sure if you agree, but I think that using sediment transport models might be not very suitable for microplastics. And for creating specific microplastic models, we need more parameterization of basic and complex processes. So we need more parameterization of the particle properties, of the settling and rising velocities, and of the resuspension. And if we look at more complex processes, we also need to include aggregation with sediments. We need to include biofouling, and we need to include fragmentation and beaching. So how many of the particles are held back on the riverbanks, for example, or in vegetation. Yeah, so I'm sorry. This lecture, I think it was supposed to give some answers, but all I do is raise more questions. But that's just how it is in microplastic research. So it is quite a new discipline, and especially when we compare it to sedimentology, which is, well, it is awesome for the researchers because there's so much we can look at, but it also means that we simply don't know that much. But how can we relate what I just told you to research goals? We identified in our paper 4 research goals related to the transport behavior. We have, first, we need to understand and quantify interactions with environmental substances and influences and their impact on microplastic transport. Then we need to evaluate the vertical distribution of microplastic particles and their transport in the water column. We also need to evaluate the differences between the resuspension and the deposition behavior between microplastics and sediments. And we need to understand and quantify the impact of biota on microplastic transport. We also identified 2 more research goals, but for that I would like to refer you to our paper, which will hopefully be published soon. I will definitely link to it in the comments on YouTube, where we also talk about standardized sampling methods and the toxicity of microplastics in comparison to natural sediments. Now, what are the important points that I want you to remember from this talk? There's still a lot to do. we are still a long way from fully understanding microplastic fate in the aquatic environment. And I've just talked to you about rivers, but rivers are just one environment. We all know that there are other processes govern the transport in other environments. And we need to understand the transport in all of them. So the aquatic, the terrestrial, and the aerial transport to solve the mystery of the missing plastic. So now, based on what I just told you, what do you think? Are microplastics just artificial sediments? And can we learn from natural sediments? Or do we need to start at the beginning? And with that, I would like to thank you very much for your attention, and feel free to reach out if you have any questions or want to collaborate. And I'm looking forward to the discussion.
Perfect. Thank you. Thank you very much, Kryss. This is really interesting, and I had no clue about plastics. I just realized. So thanks a lot. Does anyone have any questions? Please unmute yourself and perhaps while people are gathering their thoughts, I have a question. So you described in one of your earlier slides the shapes of plastics and the sizes, and I guess they must be correlated, because as plastics degrade, I imagine their shapes become easier or less complex.
Yeah, we think so, but we are not sure yet. So that's something we should definitely look into. I mean, for sediments, we all know that they are getting rounder and rounder along the river. We're not sure if that's the case for microplastics. So we can't see a trend in decreasing grain size for microplastics, because I mean, there are always new microplastics coming in the river. Which is just different from sediment transport.
Thank you. I see that William Nardin had a question in the chat. I can read it out loud. Great talk, and thank you for sharing. I'm wondering if particle tracking models might help to mimic plastic particles' fate and transport.
Yeah, we talk about that more in our paper, and I have to refer you to that because I'm not the expert on that. There are some studies that use it, and I think it's for a first idea it's good, but we don't really know how it's compared to the reality.
Cool, thank you. Jan Fleckenstein, can you unmute yourself? Yeah.
Yes, thank you very much for this very interesting presentation and the nice overview of the topic. I have a question concerning the modeling efforts, and you've pointed out nicely how there are so many different processes that affect how the particles move in the river or aquatic environment. Yet on the other hand, if you think of trying to include everything into a model, you also create a lot of additional efforts for parameterizations, equifinality problems. And if you were interested in larger scales, let's say export loads to the ocean or so, isn't that then also a good idea to think of trying to evaluate the relative effect of the different processes on the more macroscopic behavior of the plastics, kind of in a combination of lab experiments that you can more easily control, and then more aggregated assessments at the larger scale? Because otherwise I see the risk also to have over-parameterized models where you cannot really fully constrain the parameters and coefficients based on data that we have. Can you elaborate what are your thoughts on this would be?
Yeah, absolutely. I completely agree with what you just said. So we need to see which processes are important to include and which are not. But at the moment, we don't really know yet. So we should do that, and then we can maybe again simplify the models that we use in the future. But it's of course important if we look at small scale or bigger scales.
Okay, thank you.
There are quite some hands and questions. So Robert Eller.
Sorry, I'm coming on now. That was a wonderful presentation and a synthesis, and thank you for that. I'm very interested in bioturbation, and I'm wondering what role you think it might play in terms of determining the properties of the microplastic distributions in muds in particular, the selectivity of particles by benthic organisms so that they might either inject directly microplastic particles into the boundary layer, or they might create differential distributions right at the sediment water interface of microplastics. Do you have a sense of the role of bioturbation in that regard?
Well, I know that there is a study that creates a parameter how we can include that in models, because it's well, it is still very preliminary and we don't really know, but there's this one study that looks into it, which might be a beginning, but it is there's not much on that, so I'm sorry, I can't really give you an answer to that, but it's definitely something worth looking at.
Thank you.
Paul?
Oh, Grace, such a great talk. I learned a lot. And so the topic you see is we learn the nature of the sediment. Then we try to understand the microplastic. So now the question, because the microplastics, generally the density a little bit lower than the natural sediment. So in a river sediment, when they shoot to the ocean, sometimes when we have positive buoyancy, they have a plume, you know. So if those microplastics from the many large rivers, particularly Asia rivers, so they shoot to the ocean, those microplastics will stay much longer on the surface of the ocean than the sediment, supposed to, right?
Yeah, probably.
And this is the question. I don't know if there's any scientific conclusion. How long they will stay on the surface as a plume? Sediment will gradually settling down, but those microplastic maybe stay much longer on the top layer. Then what's the effect to the ecosystem or primary production?
Yeah, that is a very good question. We don't really know how long they stay on the surface, and I have to say, oceans are not my my primarily research topic, but there are some modeling studies that say that 99% of the microplastics will end up in the deep sea. So there are some processes that
eventually
lead to that, but I can't tell you how long it takes. And when we talk about the microplastics that come from rivers, there's also the estuaries in between that might be huge accumulation zones for microplastics, which we also don't really know yet.
But definitely your talk is the kind of stimulate us the ideas for those oceanographers, Bob L, any other colleague. We should maybe write a proposal. See what's the role of this microplastics in the biochemical reaction, how the bacteria, like how they involve the, you know, all the kind of biochemical in the sediment and the water, and even the water to the atmosphere. That just looks like still unknown area. Maybe somebody already done, I don't know, but it sounds very interesting.
Yeah, there is quite a lot of research on marine transport of microplastics in Utrecht. So maybe Jaap knows more, I'm not sure, but.
I definitely don't. Sorry, no. There's a professor, I think Eric van Sabile, who does a lot of research in plastics in the ocean, but I don't. Unfortunately, I have another question in the chat first. Sorry, William, and then I'll get to you. But thanks, Kryss, for the interesting presentation. Could you please elaborate more about numerical modeling for microplastics? What kind of software is used? Any research related to it already?
Sure, I can elaborate a little bit. Again, it's I haven't done any modeling myself, well, at least not at a scale that would be worth mentioning here. I know that Lechthaler in the Netherlands is working on including microplastic transport in DEF 3D, which would be very nice. And then there are some other models. We have one at Wageningen University that's used for microplastics that also already includes some of the transport processes like aggregation. But I'm not sure what else I could tell about that right now.
Well, thank you. William?
Yeah, so again, a very good talk. Thank you very much for sharing all this information. And in the recently, like in the last couple of years, we start to work here in Chesapeake Bay, University of Maryland, and something that I didn't see like in your talk, and I think it's still related with the sediment characteristics. It's and this is regarding the degradation of the plastics, and what we saw, like there is a huge feedbacks between like sandy sediment or cohesive sediment, because like for abrasion or other processes, there's really, it's not only I agree with you that it's for the fit and transport, it's hard to relate microplastic with sediment because it's completely like a different physics. But then there's also all those secondary feedbacks. These are really interesting in if you are looking like with the microscope on cracking, on different degradation on those strips of depending on also like on the different types of plastic. I think it's really interesting. Thank you for sharing all this information on the physics and settling velocity. It was really cool. So I'm wondering if you are aware of any of those studies that are looking also at feedbacks with the sediment characteristics.
Yeah, so at old university at AWTH in Aachen, we started some experiments on the degradation and the contact of microplastics and sediments and waves. I think there's a first review paper on that published now, but not a result of the studies. But I can talk to my colleague and see if he has anything yet. But I agree, it is very interesting also to see about the degradation, and it's definitely interesting.
Thank you. Any other questions? I see. Sorry, Jan, go ahead.
I just had one other question concerning processes that affect the transport. You hadn't mentioned interactions with organisms, and there's some studies that show that, for example, for lakes, the uptake of particles of a particular size can then end up in the organisms that move it around in the lake, and then they excrete it, which also then it gets excreted and coated in the feces, and then can sink while it might otherwise be buoyant, for example. I mean, that's not so relevant probably for rivers, but they might have filter feeders like certain mussels that may take it up. Have you encountered those kind of processes or effects in the work that you've done, or do you have any thoughts on this, how relevant this might be? I mean, it's definitely also a question of ecotox and exposure, but also for the transport, it might be interesting in some cases.
Yeah, no, I only read about that for lakes and for the marine environment, especially with marine snow. It's quite common, but for rivers, I've never read anything about that, and I'm not sure. I'm a civil engineer, so I don't really know anything about biota. I'm just starting to learn on that, so unfortunately, I can't tell you anything.
Okay, thanks.
Perfect. All right. Thank you then, Kryss. If there are no further questions, thanks everyone for attending. And hope to see you again next week. Thanks again, Kryss. This was really interesting.
Thank you so much.